Well, hello again. What we're going to talk about right now are reducing valves, and then we're going to also talk about regulators. Remember, we've talked about some of our equipment. We've talked about the cylinders. We're going to talk about how do you deliver gas to a patient. You have to have a way of getting it out of the cylinder safely. And basically, these are the reducing valves, and these are also the regulators that we deal with. So basically what they do is they take your high pressure down to your working pressure. And if you remember, the high pressure can be as high, depending on the size of the cylinder, can be as high as 2200 psi. If you have a larger cylinder, then you can have more pressure in it at that particular point. We have to get it down to our working pressure. Remember that working pressure is 50 psi. You have reducing valves that are single stage or multiple stages. Most of the time in the hospital, you're just going to use a single stage. We really don't need the cost or the precision of that. So that's why we can get away with the single stages. If we're using one that is multiple stages, it reduces that high pressure to about 200 psi, and then it takes that 200 and brings it down to 50. And there's two opposing forces that are working here. You have the little, if you look in the book, and you'll see it here anyways, the little picture of your reducing valves. There's a little diaphragm, and that diaphragm either goes up and closes the poppet valve to stop the flow of gas into it. Once the gas is out, then it'll drop, and that opens the poppet valve and allows the gas to go into it. So it's just a matter of working, letting the gas in and having it either open or closed at that point. And as you can see, this is basically what it looks like. You have a spring with a single stage. You can adjust that if you need to. You can see the inlet at that particular point with the nozzle. And you can see that if we go ahead and allow the diaphragm to go up, then the poppet valve will actually cover that nozzle. And then once we let the gas out through the outlet, then the diaphragm will come down and open up the poppet valve again. And another one's adjustable. We can adjust the poppet closing spring if we need to. Very simple device, but it works extremely well. Multiple stages for the most part. There you have it, two single stages in a series. So you can see those two. The first stage, as I said, reduces it to 200, the second to 50 psi. And you do get more precise regulation, but it's not one of that in the hospital that we really need. And there you can see you have the springs, the two of them together at this particular point. How do we know it's a multi-stage? We're actually looking for the pressure relief valves because each of these is going to have its own pressure relief, and the book will also tell you each of these will have its own poppet valve, and that's how we know that we have more than one. So what are some of the safety features? They do have pressure relief valves. Remember, we find pressure relief valves on the valve stems. We find pressure relief valves on our ASS, PISS, our devices also to make sure that we don't have a problem with our cylinders or we don't have a problem with the equipment that we're using at that particular point. We also have some pop-off valves that will do the same thing for us. And then the index of the inlet and outlet is another one. You need to remember that the American Standard Safety System is for your large cylinders, F and above. Your pin index safety system is for E and below. What these are designed to do, and I know you've heard this before, but you need to remember, prevent people from putting the wrong reducing valve or regulator on a cylinder so that you're not delivering the incorrect gas to your patient. That's why these systems are there, is to prevent problems with your patients, and that's one of the things that we need to remember. So regulators, for the most part, they regulate both the pressure, and they do this because they have a reducing valve with them. They also have a flow meter which controls the flow. So a regulator is actually two devices in one. It's a reducing valve which reduces the pressure for us, and it's a flow meter which allows us to deliver that gas to our patients. And we can read the pressure from the pressure gauge of the reducing valve so we know exactly how much is in there. Typically, these gauges are board-on gauges. Remember, board-on gauges are round gauges. And because they're round, that's why they have that name, board-on. And so most of these reducing valves, when you see them, are board-on gauges. So flow meters are designed to deliver that gas to that patient. And we can have a board-on gauge that's also a flow meter. And it says here it's a fixed orifice. A fixed orifice is the size of the outlet. It's a small hole, and it controls the amount of gas that can flow out of it. One of the things that we have in the lab is we have a board-on gauge, and it's actually a regulator, and it has two board-on gauges. It has the pressure reducing valve and the flow meter to it. If you hook it up to a 50 psi source, you can't get the flow to go through it. And one of the reasons people ask me, well, why do you keep this? Well, I keep it because I want you guys to look at your equipment. You have to learn to look at your equipment before you start using it. And so what happens with this, especially when we're actually, this is right now, it's a reducing valve. We'll hook it up to our ventilators because we run our 50 psi to the ventilator, so we just have to use a reducing valve. And the students will sometimes hook it up and they can't get it to work. And normally what I'll do is make them take it off, look at it, and then they can change it. But you've got to get used to looking at your equipment. You need to make sure your equipment is what it is. You also will see an uncompensated Thorpe tube. The needle valve is proximal to the Thorpe tube. We don't normally see these in the hospital. If you ever see one, it's probably in some lab somewhere, but you should not see any of these in the hospital. And then the compensated Thorpe tubes, these are the ones where the needle valve is distal to the Thorpe tube. These are what we use when we're delivering our gases to our patients. So all board-on gauges measure pressure. So why do I tell you that? Because there's a question that I always ask, what is it that a board-on gauge pressure measures? And the answer is it measures pressure. We calibrate it to read flow when we're using them as flow meters. What we've done is we've taken the dial off the front of it, the face, and changed it so that it's reading the liter flow at that particular point. So boron gauges are true pressure measurers. The opposite is true for the Thorpe tubes. Those are flow measurers, okay? So basically with the board-on gauge, the gas is going to flow past that reducing valve, past the board-on gauge, out the fixed orifice at this particular point in time. And there you see it reads the pressure and it's calibrated for flow. If you obstruct this, if there's a downstream obstruction, what's going to happen is that it's going to read higher. It looks like the flow meter is higher than it actually is. This is one of the reasons why when we're using cylinders and transporting patients, we don't want to lay the cylinder on the bed. One of the things that can happen if you're not careful and you lay it on the bed, it can go flying off the bed, and that's the last thing you want to see is a cylinder making its way down the hall because the valve stem broke. It's kind of hard to say you didn't do it when you're the only one there left in there. Anyways, what you have to make sure you do is we want them upright, and then we want to make sure that whatever piece of tubing is attached to it, that particular board-on regulator or reducing valve, it's not being compressed, okay? How do tubing get compressed? It's very easy. What happens on occasions is that people will have the patient in the bed, they'll put the cylinder on the bed. They'll put the sides up, and when they do, they don't notice that the tubing that's going from the cylinder reducing valve or regulator, actually the regulator more than the reducing valve, is going to the patient, has been compressed between the mattress and the bed rails. And then they're looking, going, oh, wait a minute, this is only supposed to be 2 liters. It's reading 3, and they'll turn it down. In reality, the patient's only getting 1 liter. But this, you can see, very, very simple device. There you have a gear mechanism, coil tube. As the gas comes in, the tube goes around and comes down. And then as you use the gas, it comes back down. And there you can see the gear mechanism, all of that good stuff again. This is an aluminum regulator. This is a reducing valve. People go, yeah, but there's only one board-on gauge. That's true, and that's the board-on gauge. The flow meter is in this end down here, okay? And this is a pin index safety system. Remember, we call this the yoke system, the pin and yoke system. And that's what you're seeing with it. Remember, with the aluminum regulators, if you over-tighten them, you can bend them. If you bend them and you turn them on, you can actually blow them up. So you want to be careful with these. Sometimes these flow meters only go up to about 8 liters. You on occasions do have some that go up to 15. Most of the time when we're taking care of our patients, we always want to make sure that we know the highest flow for the regulator, because sometimes those patients need those 15 liters. If we just go in and grab one and it only goes to 8, your patient is still missing a lot of flow at that point. So the uncompensated Thorpe tube, it's a V-shaped tapered tube, has a float inside of it, and it has a needle valve, and the needle valve is proximal to the Thorpe tube. It's in the, and as you can see, it's talking about the pre-measuring tube. It has a variable orifice. Well, why is that? It's because I can deliver flows at different liters per minute. I can go half a liter all the way up to 15 liters. And so the orifice has to be able to adjust for the flow that's coming through it. Now, one of the things you always have to look for, and like I said, we most of the time use the Thorpe tubes, the compensated Thorpe tubes in the hospital, not the uncompensated ones. If you get a flow meter that only goes up to, say, 5 liters per minute, it's a Thorpe tube, look at it, because you're going to see it's calibrated differently. Instead of half liters, like a half, 1 and 1, 1.5, 2, 2.5, 3, you're going to see 1/16, 1/8, 1/2, 1/4. Those belong in the nursery. Okay, when we're delivering oxygen to the patients, and we're going to talk about this when we talk about oxygen, we have to watch how much oxygen we give the babies, especially the preemies and the low birth weight babies, because we can cause a lot of damage to them. So if you see something like that and you're on the adult portion of the hospital, gather them up. They have to go back to the nursery. They do not belong in the adult floor. The float is going to indicate what the flow rate is, and the needle valve is actually going to adjust the flow for us. So this is the non-compensated Thorpe tube. As you can see, here's the Thorpe end of it. This is the one that's going to go into the disc outlet. Here's the needle valve. This needle valve adjusts and opens up the amount of flow that's coming out to that patient. This is pressurized. This little area, if I could show it to you, but I can't, but this little area between here, let's grab my pen here. This tiny little area between here and back here is 50 psi, okay? Once you get down here, this is no longer 50 psi. This is only the flow that you're putting in to this Thorpe tube, okay? With the compensated Thorpe tube, the needle valve is now distal to the Thorpe tube. It's further away from it. As a result of that, the pressure within the tube equals the line pressure, or 50 psi. I have 50 psi going through that entire flow meter at that particular point. With the uncompensated Thorpe tube, remember the back pressure affects the bourdon gauges. They read higher. With the uncompensated Thorpe tubes, the pressure actually with back pressure reads slower. So you turn the oxygen up, and that would not be good for the patient. With the compensated Thorpe tube, it's going to read exactly what it's supposed to read. If you've cut off the flow, it'll show zero flow. So there's three ways to tell if it's compensated, and this should be in the addendum, plus what I'm going to tell you, and I'll try to show it to you on the next slide also. The first one is if we look at it, we should be able to see where the needle valve is. When we pick these things up, we can see the Thorpe tube, we can see the needle valve, and now we know exactly where that is. Another one is that when I plug this into the disc outlet, the float jumps. Because this entire tube is 50 psi, that 50 psi when I plug it in goes into the flow meter and it causes the float to jump and then it falls back down. And then the third way, and this is the hardest one, you have to read the flow meter. It'll actually say calibrated at 50 psi. It will tell you it's compensated. It will tell you all these different things so that you can tell that this, in fact, is a compensated Thorpe tube. So here's the picture. Here's your needle valve. Remember that needle valve was way over here on the uncompensated one. Now it's way over here. And if you notice, this line goes all the way around here, all the way down, and then we don't get that needle valve until you're about ready to send it out, and that's where we're going to go ahead and adjust the orifice at that particular point in time. So there's a little bit of float in here, and when you plug this in, that float jumps all the way up, and then it falls back down at that particular point, okay? So those are the two ways you can do it. And then the third way is that it actually says on the side of the flow meter that it's calibrated. So it's pretty easy to find those things. When we look at blenders, lots of folks say, can we make a margarita at work? The answer is no. Unfortunately, but these are blenders. They're also called proportioners. When you see them at the end of one of the chapters, chapter 1 and why it's hardback, they'll ask you, what do you call them? And the answer is proportioners. What they basically do, in order to run a blender, you have to have both an oxygen and an air source. You have to put 50 psi of each of those into the blender, okay? And the blender can either give me anywhere from 21% to 100%. It can provide the flows that I need, the high FiO2s, and it works really, really well for us. The nice thing about the blender is it helps to give us a more precise control of what the FiO2 is that the patient's getting. Most of the time, if you're in the nursery, you're going to see that the babies actually have their oxygen hooked to blenders. And the reason is we can actually control that, okay? In our ventilators, we also have blenders that helps us control the FiO2 going to that patient. And when we talk about the CPAP, BiPAP machines, those also have blenders in them. So they're able to control that oxygen to make sure we're not giving too much, too little to the patient at that particular point in time. So there it is. You have to have both of these. When you're hooking a blender up, if you hook up the air first, it's going to alarm. It's going to alarm really loud because you're missing the oxygen. Once you hook the oxygen to it and you have both of them hooked up, the alarm silences. One of the therapists that we have was working in the nursery. It happened to be her first night in the nursery. She goes down there. These alarms are going off. The nurses are all panicking. These are babies. Got to do something with the babies. And what had happened is that the piping system for the oxygen had shut it down because it wasn't maintaining the pressure. And so she had to call her boss, who brought her a cylinder, and they were able to feed it through the zone valve and get the line repressurized for the nursery. So basically, there's two chambers, opposite side of a diaphragm again. You dial in the control, and that's where the proportioner valve works. And so if you look at it, here's your air, There's your oxygen. So here's your 50 psi. Here's your 50 psi. You're going to go ahead and adjust this, and as you adjust it, you're going to open up one and close the other. Just depends on how much oxygen you want to do at that particular point. Now, probably a good way of thinking about this is your shower. When you go to get into your shower and you want to take a shower, you turn it on all the way to the hot. Well, that's way too hot. That's your 50 psi of air, okay? So you want a little bit of cool water in there, and that's where your oxygen would come in. And so what you're doing is you're adjusting the valve so that you get a much better mixture and a much more comfortable shower at that particular point. Heliox, again, remember we can run it through the O2 flow meter, but we have to adjust the calibration for it. So it's based on the density. Heliox is the second lightest, helium is the second lightest gas we have. It's accurate with the O2 and air. That's what the flow meters are for. However, the Heliox flow meters are very expensive, and there's your flow factors for each of those. And there's a way to go ahead and correct flow at altitude. Most of the stuff you're going to buy should already be corrected, but on occasions you get strange things sitting in your department. You're not quite sure where they came from. So basically, as you go up, the density of the gases are still the same, but the pressure is less. Because the pressures are less, you're delivering different flows. And basically, here's a nice trivia question for you. You know, how does it change? And you can see 1% for each 1,000 feet from sea level. Actual flow, how do you find it? You take the indicated flow, say 5 liters times 760, because that's your barometric pressure at sea level, and divide it by the actual barometric pressure. If this were Denver, you could say 5 times 760. Let's see if we can do that. 5, I'm not very good at this, but this times 760 divided by 600, which is Denver. Gives you roughly 6.3 liters. So your patient's actually getting a little bit more than they normally would at that particular point in time.